In this video we're going to talk about common ion effect. We saw this in our last unit, but now we're going to apply it to acids and bases. So when we talked about it in terms of our KSP, or solubility of salts, right? The decrease in solubility of an ionic salt in solution because one of the ions was already present, right? And we saw that when we did our KSP. So according to common ion effect, if one of the ions is already present, then less salt is capable of dissociating, so that the solubility is lowered, right? So it's going to be less soluble. And the same thing happens for acids and bases. So we decrease the acidity or the basicity by adding in a common ion. So we can see that if we look at this problem here. So we have to calculate the concentration of hydrogen, pH, percent dissociation of HF in a solution that contains 1 molar HF and 1 molar NaF. So again, we set up our acid dissociation, where HF dissociates into hydrogen ions and fluoride ions. So we set up our ice chart. We have 1 molar HF to start with, and none of the hydrogen, but this time we're going to have some fluoride. Again, here we have 1 molar of our fluoride. Our reaction will still shift to the right because we need to produce some hydrogen ions, and so we'll get 1 minus X, X, and 1 plus X. We set up our Ka expression, so Ka is our hydrogen times our fluoride over our HF, and so we plug in what we know. We know our Ka is 7.2 times 10 to the minus 4, and that's going to be equal to X for our hydrogen times 1 plus X for our F minus over 1 minus X for our acid. And again, we'll use our solvers to solve, and we plug that into our equation. And we get that. I think that's right. Let me double check my equation. And we get 7.19 times 10 to the minus 4 molar. And that, of course, is X, which is equal to our hydrogen concentration. And then to find our pH, we take the negative log of that. And we get 3.14. Alright, so you can pause and do the practice problem and then come back and we will look at it together. Alright, so again we're going to take our HCN, dissociate it, set up our ice chart. We have 0.5 molar HCN and 0.25 molar cyanide ion, no hydrogen, minus X here plus X on the right. So at equilibrium we have 0.5 minus X, X, and 0.25 plus X. Set up our Ka expression, which is our hydrogen times our cyanide over our hydrogen cyanide, or hydrocyanic acid. And then we get our Ka is 6.2 times 10 to the minus 10. That is equal to X for our hydrogen, 0.25 plus X for our cyanide, over 0.5 minus x for acid. And plug that into the solver. And we get x is equal to 1.24 times 10 to the minus 9. Again, that is our hydrogen concentration. To find our pH, your negative log 1.24 times 10 to the minus 9. And we get 8.91. So in this case, we have a high enough concentration of our conjugate base to make it a basic pH. Alright, so let's move on. Next up, we're going to talk about buffers. You may have heard about buffers before in terms of blood. Blood is our most well-known buffer. It helps to maintain the pH in our bodies. Right? And so a buffer solution is one in which the pH of the solution is resistant to small additions of acid or strong base. Buffers usually consist of a weak acid and its conjugate base in relatively large and equal quantities. Okay. Calculations are based on the equation for ionization of the weak acid in water, right, forming, of course, the hydrogen or hydronium ion and the conjugate base of our acid. Right? We're familiar with this equation. Okay. So the buffer system can be made by mixing a soluble compound that contains the conjugate base and a solution of the acid, such as sodium acetate and acetic acid, where this, of course, is your acid and the acetate ion is your conjugate base. Or you can do a base like ammonia and its conjugate acid, which is the ammonium ion. Okay. And if we know the Ka of the acid, the amount of acid and the amount of conjugate base, then the pH of the buffer system can be calculated by using what is called the Henderson-Hasselbalch equation. And the Henderson-Hasselbalch equation is how we can find the pH. We get pH equals the pKa plus the log of base concentration over acid concentration. Alright? And I believe this equation, yes, is in your reference packet. Right? It is right here. The pH equals pKa plus the log of base over acid. Now they use conjugate base and acid here, but as long as you can identify what's the base and what's the acid. Okay? So we're going to look at this problem here. A buffer solution was made by dissolving 10 grams of sodium acetate in 200 milliliters of 1 molar acetic acid. Assuming the change in volume when the sodium acetate is added is not significant, estimate the pH of the acetic acid acetate buffer solution. And the Ka is this. So again, we can use this equation. So we know the Ka. To find the pKa, remember that's just the negative log of our Ka. Right? And then we say plus the log of our concentration of base divided by acid. So base, of course, is our acetate. Right? We have 10 grams and 200 milliliters. So we would need the concentration of acetate. So our concentration for our acetate we would find by, of course, changing grams into moles and then dividing by liters, right? So we have 10 grams and we put that in 200 milliliters. So we need to do a conversion where we change our grams to moles. So 1 mole, this is sodium acetate here that we have the 10 grams of. So we have to include the sodium. carbons, 3 hydrogens, and 2 oxygens, and that's an 82.034 grams. And then we have our moles. Right, so now we need to change our milliliters to liters. Just 1,000 milliliters for 1 liter. Right, and then we'll have our molarity. So 10 times 1,000 divided by 82.034. Divided by 200, forgot by 200, equals 0.610 molar. So that's our acetate concentration. Our acetic acid concentration is 1 molar. So we have our 0.6, our base, over our acid, and then we solve for our pH. So we do negative log of 1.7 times 10 to the minus 5 plus the log of 0.610 over 1, and we get a pH of 4.55. Okay. Alright, so you try the next one, and then come back, and we'll look at it together. Alright, so we have a buffer solution. We have, again, 0.5 molar acetic acid and 0.5 molar sodium acetate. Again, the acetate part is our base, and the acetic acid is our acid. So again, to find our pH, we would do the negative log of our Ka plus the log of base over acid. So our base is 0.5 over our acid, which is 0.5. Right? And the log of 1, we all know, is 0. Right? Because anything to 0 power is 1. So in this instance, when your acid and your base concentration are equal, then your pH is equal to your pKa. So you get the negative log of 1.8 times 10 to the minus 5. And here we get 84.74. Okay. So I know I have the Henderson-Hasselbalch equation again up here, because originally I would have done those problems without the Henderson-Hasselbalch, but I think it's just easier to go right into doing it since we've already done common ion in the previous unit. So let's just use our Henderson-Hasselbalch again and do another example here. We have sodium lactate and lactic acid. Again, our pH is going to be equal to the negative log of our Ka plus the log of our lactate over our acid, and we plug that into the calculator, and we get a pH that is 3.38. Alright, let's look at a base. This problem here is a base. So we have our base concentration, we have a Kb, and then we have the concentration of our conjugate acid. Alright, so you don't have to do anything really differently for a base than for an acid, except that the equation uses Ka. So we would find the Ka here, and we would do that by doing 1 times 10 to the minus 14, the Kw, divided by the Kb, and we find that the Ka is 5.6 times 10 to the minus 10. Or, if you have a chart, you can look up what the Ka is for the conjugate acid. You can do that too, but on a tester quiz you wouldn't have that. So then we would have the negative log of our Ka, which is 5.6 times 10 to the minus 10, plus the log, again it's base over acid, right? So base is our ammonia, is 0.25 over acid, which is 0.4. And so then we plug that in. And we get 9.05. Okay. And so this next problem is just an example of how to calculate the ratio of the ammonium chloride to ammonia that's required to make a buffer solution with a pH of 9. So here we're told the pH. We know our Kb, and of course in the previous one we found the Ka was 5.6 times 10 to the minus 10. Right, and I want us to calculate this ratio. And so we find our pH is 9, right? And so that's going to be equal then to the negative log of 5.6 times 10 to the minus 10 plus the log, again, of base over acid. So that would be NH3 over NH4. Right? And so then we would solve for that. So to do that, we would take 9, we would add the log of 5.6 times 10 to minus 10, and that gives us a negative 0.2518 equals the log of our ratio here, which is x. So to get rid of this, we do inverse, which is 10 to the, right, or second function log for that answer, and we would get that x is equal to 0.56. Now, this is equal to this ratio, which is NH3 over NH4 plus. And this asked us for the ratio of NH4 to ammonia, right? So the difference there is just the reciprocal. So this would be equal to 1 over x, right? So we just do 1 over x, and we get the ratio that they actually asked for is 1.79. Okay. So let's look at this last one here. So we calculate the ratio of lithium nitrite to nitrous acid that's required to make a buffer solution with a pH of 3. So again, we know our pH is 3. It's equal to our negative log of our Ka plus the log of our base to our acid, right? Okay. And then we solve. And we get that ratio is equal to 0.71 in this instance. Alright. We can calculate the pH of a buffer solution after we add some small amounts of acid or base. Remember, they are resistant to this change. So, what happens is we end up we end up decreasing the amount of base present, right? And we see an increase in the amount of acid present. So it's kind of shifting, right? It's like the Chatelier's principle, right? Okay, so because we're going to add strong acid, so it's going to shift this way, so we're going to see a decrease, right, in your base and an increase in your acid. Chatelier's principle shift, right? And so what we have to do is calculate that change, right? What happens? So if we want to know the pH when we add 0.1 molar HCl to 1 liter of our buffer solution. So when we add our HCl, we're adding H+. Now, what is that going to react with? The acid or the base, right? It would react with the base. And it would make more conjugate acid, okay? So if we have 0.1 molar of our strong acid, and we have 0.25 molar of our base, and we had 0.4 molar, right? So setting up our ice, right? And then this, of course, is limiting, so we would change by 0.1. Change by 0.1, this would add 0.1, right? So our base decreases by 0.1 molar, where our acid increases by 0.1 molar. And then, to find the pH, of course our strong is consumed. To find the pH, we simply use our Henderson-Hasselbalch. So we know from our previous problem that our Ka for this is 5.6 times 10 to the minus 10, plus the log, again, of base over acid, so 0.15 over 0.5, and then we calculate the pH. So the negative log of 5.6 times 10 to minus 10, plus the log of 0.15 divided by 0.5. And we get a pH of 8.73. Right, so basically we're doing a little bit of an ice chart. Some of you may be able to do it without the ice charts. Some of you may not, and that's fine. Do what you need. Alright, so let's look at another one. We're going to calculate the pH of a solution when we have 0.1 moles of HCl added to 5 molar and 5 molar, and it's 1 liter, so that's the same as 0.1 molar. Right, we do have to have the same units. So in this case, we're adding our acid to this buffer solution. So we have our strong acid as our hydrogen ions. It's going to react, of course, with our base, which in this case is our acetate ion, and we're going to form more acetic acid. And so we set up our ice. We start with 0.1, 5, and 5. We're going to consume all of our 0.1. Right, it's going to react with some of that, and we're going to make more of the acid. So this is going to go away. We're going to be left with 0.49 molar, and we're going to be adding to this at 0.51 molar, or 5.1 molar. Then we plug in our Henderson-Hasselbalch. pH equals the negative log of our Ka, which is 1.85 times 10, 1.8 times 10 to the minus 5, plus the log, again, base over acid, 4.9 over 5.1. And then we plug that in, and we get .73 for our pH. Alright, so you pause and try the next one on your own, see what you get. Alright, so again we have our acid reacting with our conjugate base to make more acetic acid. We have 0.1 mole, again still in 1 liter, so that's 0.1 molar. This time we have 0.05 molar, 0.05 molar. Again, we're going to use up all of our acid, minus 0.1, minus 0.1, plus 0.1. So we have no strong acid left, and over here we're going to have nope, we're not. Sorry. Now this time our acetic acid is our acetate ion rather is our limiting factor. So we would change by that 0.05 minus 0.05 plus 0.05. Sorry about that. And so 0.1 minus 0.05 leaves us with 0.05. None of this, and over here we get 0.1. But in this instance, since we have a strong acid remaining, we only use the strong acid to find our pH, because pH is always the negative log of the hydrogen concentration. So it will be 0.05. So we do negative log of 0.05, and we get 1.3. I need to fix that one. Make that more like the other ones. So it's not that strong acid isn't the one that's limiting, or is the one that's limiting. Alright, so we'll do more problems like that in class tomorrow. Alright, next we have our buffering capacity, just a real quick piece on that. The buffering capacity talks about how the amount of protons or hydroxide ions that the buffer can absorb without changing the pH significantly. A buffer with a large capacity contains large concentrations of the components. Again, a large amount of acid and conjugate base, or base and conjugate acid. The capacity of the buffered solution is determined by the magnitude of that. And since large changes in the ratio of base to acid will produce large changes in the pH. We want to avoid that. And we avoid that by making sure that the concentrations are high and equal to each other, right? So we want that ratio, optimum ratio then is a 1. Okay, that would be the most resistant to change. Alright, so one last problem here. A chemist needs to make a buffered solution that has a pH of 4.3. Can choose from any of these. So calculate the ratio that we require for each system to produce a 4.3, and which system then would work best, right? So if we think about that, right, the pH is equal to the pKa plus the log of base over acid, right? And if we want this ratio to be 1, we're essentially saying we want this factor to not matter, right? And so what we're really looking for is the optimum buffer for that situation would be the one where the pH is equal to the pKa. Okay? In this instance, we don't have one that is going to necessarily be directly equal to that. So if we find that, right, find the pKa of each one. So we get negative log 1.35, 10 to minus 3. Here we get 2.87. The pKa here, negative log of 1.3 times 10 to the minus 5 gives us 4.89, and a pKa here of negative log 6.4 times 10 to the minus 5, we get 4.19, and then pKa here is 7.46. So we can eliminate the first two, right? And then these two are fairly close to 4.3, right? Or we want the one which is closest to it, right? And so the one that's closest to 4.3 would be our 4.9. So the benzoic acid would be the one that would be the most optimum buffer for the situation that we're looking for. Right, and so that is the conclusion of today's video.